All right, I'm going to be going over a few questions here as part of our review for our midterm. Feel free to pay attention right now, or you can just access this a little bit later on YouTube. Question 17, so this is all work, energy, and power. Question 17 reads, a rope is attached to a sledge, and a boy uses the rope to pull the sledge along a horizontal surface with constant velocity. The tension in the rope is 100 newtons, and the rope is held at 30 degrees to the horizontal. How much work does the boy do on the sledge when he pulls it a distance of 5 meters along the surface? All right, the first thing that's perhaps helpful in solving this is to know that the equation for work is force times displacement times the cosine of the angle theta between them. Remember, that's the full form of this equation, and we need it here because not all of this force is in the direction of displacement. So the component of force, F cosine theta, that goes in the direction of displacement is the one that contributes to work. Because we know the force is 100 newtons and the displacement is 5 meters, the angle between the force vector and the displacement vector is given as 30 degrees. If you know your equations, a question like this, you can make really short work of, right? If you don't know that equation, if you forget the cosine theta part of it, you're going to incorrectly choose towards D, right? You just do 100 times 5. But if you do 100 times 5 times the cosine of 30, you will get 433, which is very close to 430 joules. And the correct answer to this one. Moving right along, we have the kinetic energy, E sub k, of an object of mass m moving at speed v is given by the equation shown. Kinetic energy is 1/2 mv squared. That's an important one to have in your list of equations. Which equation is not used in the derivation of this equation? So let's remember where this comes from. It comes from really the definition of work. Work and energy kind of the same thing. And so if we start with work is force times displacement, and then we remember that force, according to Newton's second law, is mass times acceleration times displacement, then we're really considering sort of arriving at this equation by replacing what acceleration is equal to in terms of this equation. And so if we rewrite this equation, v squared minus u squared over 2s, you got really good eyes and you can read that, that equals a, we plug that in for acceleration, and we get mass times v squared minus u squared over 2s. All right, that's what acceleration is according to this equation of motion. Times the s out here. Then the s's will cancel, and we get distributing the mv squared over 2 minus mu squared over 2. And if the initial velocity is 0, then that can kind of just go away, and we'll get the equation for kinetic energy. Note that we needed the equations A, C, and D to derive that, and so the correct answer, which equation is not used, would be D. This is just, remember, non-accelerated motion. Displacement equals velocity times time. The last one here says a grasshopper of mass 0.12 grams jumps vertically. It uses its back legs over a time of 0.020 seconds to jump, leaving the ground with a velocity of 3 meters per second. What is the average power developed by the legs of the grasshopper? These are the sorts of questions that are very pressing and important for physicists to determine. Yeah, what's the power in this grasshopper's legs? Power is the rate at which work is done. And remember, work is the same thing as energy. It looks like this grasshopper is converting some elastic potential energy, like the conclusion that you're working on, hopefully, from their legs into kinetic energy of motion. And so I'm really just going to consider the kinetic energy that this grasshopper is able to sort of develop, because I know how much time it took, right, over time at 0.02. So here, really, the work is the energy. Remember, we started with the definition of work to get this. And so I'm going to calculate the energy 1/2. Now the mass is 0.00012 kilograms. That's a tricky thing because 0.12 grams is 0.00012 kilograms. You have to convert this to kilograms in order to express watts of power. Take a look at the video on base units where I kind of go over all the base units of work, energy, power. The velocity was given as 3 meters per second squared. I can kind of put that in there like that. And then all of that over the time that it took, 0.02 seconds. So we have kilogram meter squared per second, which are kilogram meter squared per second cubed, which are the base units of watt. And if you type all that in your calculator correctly, you should be able to show that the correct answer is, I think it's C. Let me just double check. 0.5 times 0.00012 times 9 divided by 0.02. So it's 0.027, which is the same thing as 2.7 by 10 to the negative 2 watts of power in a grasshopper's legs. Until next time, this is Dr. Schleif.